Okay, so coming back to the complexity, it's time also to speak about uncertainty, because you may imagine the high degree of uncertainty that this kind of modeling approach can generate. So Ulrich will tell us how to possibly address this.
Do we have a pointer here?
I think it's not working. Okay. This is the only.
No pointer.
No.
Okay. Okay. Fine. Okay. Yes. Hello. So I will talk a little bit about uncertainty analysis, just to give you back a little bit the overview. I don't know if the mouse doesn't work. Okay. So there on the very right, in the yellow ellipse, you can see the GIS uncertainty characterization, and this is what I will focus on. So the goal was here in the project to support in the MIMES model development uncertainty characterization of some MIMES parameters, and how to actually characterize this, because we want to take really into account spatial correlation and model different parameters spatially. So how can we derive this, and how can we also disaggregate certain parameters, because a number of parameters are more lumped, like valid for entire municipalities, but it becomes more interesting and if you can look at the spatial variability. So why might be uncertainty analysis important? So I think we have heard already in ecosystem service models, these are very integrated assessment models. So we have a lot of models which are connected to each other. They are integrated, integrating different processes at different scales, and we want to often include georeference data which also occur at different spatial scales, so sometimes at the global level more aggregated, at the detailed level at a higher resolution, but sometimes this is also mixed, and often this kind of change of support is not always taken into account. So we have maybe one value for one municipality and not try to model this also. So in conventional uncertainty propagation, this is usually not taken into account, spatial or sometimes also space-time correlation and variability. And spatial and temporal uncertainty propagation analysis can help to better characterize spatial variability and the uncertainty of input data, for example, and then hopefully also to assess ecosystem service impacts in a better way at the spatial level. So this is kind of the conventional uncertainty analysis, where we start with kind of a screening to see what are sensitive parameters, then we develop a probabilistic approach, propagate this through the model with the different sources, do a sensitivity analysis, more advanced, stochastic, and which can tell about proportions, and which can also give a feedback to the modeling. And then maybe this can be already used in decision making. So here we want to take it a little step further to go into spatial uncertainty. So where we again also have the different sources, model inputs, and we have model parameters. So everything what you can calibrate, for example, is a model parameter, and input is maybe a land use type. Different model structures, equations, and model outputs, and sometimes also we have observation data with which we can also assess the model. So when it comes now to spatial uncertainty characterization and its modeling, what we have been here developing is mainly it's based on a geostatistical approach. So it's a spatial statistical approach looking into spatial correlation patterns called autocorrelation, and there's one famous algorithm called Kriging, which is used often for interpolation, and it uses the neighboring information to actually predict at unknown locations, depending on the correlation over distance, a value. To do this, we need to analyze and model spatial correlation patterns with semi-variograms, which I will show you in a minute how they look like, and then run this through Monte Carlo simulations, so that we can create not just an average picture, what is usually done in Krieging, but with simulations we can then create different realizations, we call this, so different realities, which are sometimes a bit more erratic and should resemble more reality. This is typically conditioned on input data, so that we are not completely out of the blue. And yeah, this information can be based on the data, or sometimes we also don't have data at certain resolutions, and we need to use some expert knowledge to derive this autocorrelation function. In this case, we are focusing now on the disaggregation, on the downscaling of information, and call this area to point simulation, where we first compute a semi-variogram, then estimate this and simulate different realizations. So this is how a semi-variogram looks like. So it's basically giving you a correlation structure. When the curve starts going up and reaches a plateau, that's the maximum variability, so very little spatial correlation. On the x-axis you have the distance, and you have a couple of parameters you need to model and determine. And then you have this model, which is the basis for then simulations. And when we do simulations, and depending on the correlation structure, you always see it here next to each image, we can have different, we can create different realities. Sometimes a bit smoother, sometimes, oh, thank you very much. Sometimes a bit smoother, like here, where we have quite a smooth structure, so it's not too erratic. Here, the structures, we can see smaller islands, and if we take it a bit further, where we have more erratic structure through this, we get also more erratic structures. And here is an image where we have no spatial correlation, which also sometimes can happen for certain processes. So this is quite important to characterize this and determine the right thing. So once we have characterized this, then we can, in terms of disaggregation or downscaling, we have a higher resolution information data here at a block level, and we want to predict at a much finer resolution. Here we use Krieging. So we will get an kind of an average for this entire area, and we get also the standard deviation of, so actually the downscaling error. Now, if you want to take this further to simulations, and a case study for Luxembourg, where we have different land uses, and we want to analyze the human activity expressed in CO2 emissions, where we have only average values, and now want to distribute this with some more spatial correlation patterns. Then we can have determined here a more complex autocorrelation function. It's a nested function composed out of 3 different scales, where we have a 100-meter correlation scale for residential areas, where we have 1 kilometer scale, which is more still within cities, and then 5 kilometer on average, which is in between settlements. We can model all these situations, and then use this for simulations, and then can create different realizations. So we can do hundreds of Monte Carlo simulations, and then we get different images where you can see the different patterns of these spatial correlation structures. And then when this is added back to assigned to the emission data, then this is basically here a difference map of 2 realizations, just to show that there are differences in terms of the pattern. So it's not everywhere the same, and so you can have different realities with which you feed the model. So now to conclude, so this can then hopefully help once you can further apply this to modeling techniques and propagate this through to better assess impact of land use, land cover changes at a higher spatial resolution, and you because you can take into account this variability. And this should then also enable better testing, maybe of impacts and policies when using different territorial plans, and try to characterize some uncertainties there. and in general to account for correlation structures in space, which is often still neglected, might help here better. Okay. Was it?
Thanks.
Okay.